Finally, there are issues with privacy and confidentiality. And in public data, that usually means that the identifiers are not there and you're going to have to work at a larger aggregate level of measurement. Another option is to use data from a third party. These go by the name Data as a Service, or DAS. You can also call them data brokers. And the thing about data brokers is they can give you an enormous amount of data on many different topics. Plus, they can save you some time and effort by actually doing some of the processing for you. And that can include things like consumer behaviors and preferences. They can get contact information. They can do marketing, identity, and finances. There's a lot of things. There's a number of data brokers around. Here's a few of them. Acxiom is probably the biggest one in terms of marketing data. There's also Nielsen, which provides data primarily for media consumption. And there's another organization, DataSift. That's a smaller, newer one. And there's a pretty wide range of choices, but these are some of the big ones. Now, the thing about using data brokers, there's some pros and there's some cons. The pros are, first, that it can save you a lot of time and effort. It can also give you individual level data, which can be hard to get from open data. Open data is usually at the community level. They can give you information about specific consumers. They can even give you summaries and inferences about things like credit scores and marital status, possibly even whether a person gambles or smokes. Now, the con is this. Number one, it can be really expensive. I mean, this is a huge service. It provides a lot of benefit and is priced accordingly. Also, you still need to validate it. You still need to double check that it means what you think it means and that it works in with what you want. And probably a real sticking point here is the use of third-party data is distasteful to many people. And so you have to be aware of that as you're making your choices. So in sum, as far as data sourcing existing data goes, obviously data science needs data. And there's the 3 P's of data sources: proprietary and public and purchased. But no matter what source you use, you need to pay attention to quality and to the meaning and the usability of the data to help you along in your own projects. When it comes to data sourcing, a really good way of getting data is to use what are called APIs. Now, I like to think of these as the digital version of Prufrock's Mermaids, if you're familiar with the love song of J. Alfred Prufrock by T.S. Eliot. He says, "I have heard the mermaids singing each to each." That's T.S. Eliot. And I like to adapt that to say, APIs have heard apps singing each to each. And that's by me. Now, more specifically, when we talk about an API, what we're talking about is something called an application programming interface. And this is something that allows programs to talk to each other. Its most important use in terms of data science is it allows you to get web data. It allows your program to directly go to the web on its own, grab the data, bring it back in, almost as though it were local data. And that's a really wonderful thing. Now, the most common version of APIs for data science are called REST APIs. That stands for Representational State Transfer. That's the software architectural style of the World Wide Web. And it allows you to access data on web pages via HTTP. That's the Hypertext Transfer Protocol that, runs the web as we know it. And when you download the data, you usually get it in JSON format. That stands for JavaScript Object Notation. The nice thing about that is that's human readable, but it's even better for machines. Then you can take that information and you can send it directly to other programs. And the nice thing about REST APIs is that they're what's called language agnostic, meaning any programming language can call a REST API, can get data from the web, and can do whatever it needs to with it. Now, there are a few kinds of APIs that are really common. The first is what are called social APIs. These are ways of interfacing with social networks. So for instance, the most common is Facebook. There's also Twitter. Google Talk has been a big one, and Foursquare as well. And then SoundCloud. These are on lists of the most popular ones. And then there are also what are called visual APIs, which are for getting visual data. So for instance, Google Maps is the most common. But YouTube, something that accesses YouTube on a particular website, or AccuWeather, which is for getting weather information, Pinterest for photos, and Flickr for photos as well. So these are some really common APIs, and you can program your computer to pull in data from any of these services and sites and integrate it into your own website or here into your own data analysis. Now, there's a few different ways you can do this. You can program it in R, the statistical programming language. You can do it in Python. Also, you can even do it in the very basic Bash command line interface. And there's a ton of other applications. Basically, anything can access an API one way or another. Now, I'd like to show you how this works in R. So I'm going to open up a script in RStudio, and then I'm going to use it to get some very basic information from a web page. Let me go to RStudio and show you how this works. I've opened up a script in RStudio that allows me to do some data sourcing here. Now, I'm just going to use a package called JSON Lite. I'm going to load that one up. And then I'm going to go to a couple of websites. I'm going to be getting historical data from Formula One car races, and I'm going to be getting it from Airgas.com. Now, if we go to this page right here, I can just go straight to my browser right now. And this is what it looks like. It gives you the API documentation. So what you're doing for an API is you're just entering a web address, and in that web address, it includes the information that you want. I'll go back to R here for a second. And if I want to get information about 1957 races in JSON format, I go to this address, and I can skip over to that for a second. And what you see is it's kind of a big long mess here, but it is all labeled and it's clear to the computer what's going on here. I'll go back to R. And so what I'm going to do is I'm going to save that URL into an object here in R. And then I'm going to use the command from JSON to read that URL and save it into R, and which it is now done. And I'm going to zoom in on that so you can see what's happened. I've got this sort of mess of text. This is actually a list object in R. And then I'm going to get just the structure of that object. So I'm going to do this one right here. And you can see that it's a list, and it gives you the names of all the variables within each one of the lists. And what I'm going to do is I'm going to convert that list to a data frame I went through the list and found exactly where the information I wanted was located. You have to use this big, long statement here. That'll give me the names of the drivers. Let me zoom in on that again. There they are. And then I'm going to get just the column names for that bit of the data frame. And so what I have here is 6 different variables. And then what I'm going to do is I'm going to pick just the first 5 cases, and I'm going to select some variables and put them in a different order. And when I do that, this is what I get. I'll zoom in on that again. And the first 5 people listed in this data set that I pulled in from 1957 are Juan Fangio, makes sense, one of the greatest drivers ever, and other people who competed in that year. And so what I've done is by using this API call in R, it's a very simple thing to do, I was able to pull data off that web page in a structured format and do a very simple analysis with it. And let's sum up what we've learned from all of this. First off, APIs make it really easy to work with web data. They structure it, they call it for you, and then they feed it straight into the programs for you to analyze. And they're one of the best ways of getting data and getting started in data science. When you're looking for data, another great way of getting data is through scraping. And what that means is pulling information from web pages. I like to think of it as when data is hiding in the open. It's there, you can see it, but there's not an easy, immediate way to get that data. Now, when you're dealing with scraping, you can get data in several different formats. You can get HTML text from web pages. You can get HTML tables, the rows and columns that appear on web pages. You can scrape data from PDFs, and you can scrape data from all sorts of media like images and video and audio. Now, we'll make one very important qualification before we say anything else. Pay attention to copyright and privacy. Just because something is on the web doesn't mean you're allowed to pull it out. Information gets copyrighted. And so when I use examples here, I make sure that this is stuff that's publicly available, and you should do the same when you're doing your own analyses. Now, if you want to scrape data, there's a couple of ways to do it. Number one is to use apps that are developed for this. So for instance, import.io is one of my favorites. It's both a web page, that's its address, and it's a downloadable app. There's also Scraper Wiki. There's an application called Tabula, and you can even do scraping in Google Sheets, which I'll demonstrate in a second, and Excel. Or if you don't want to use an app, or if you want to do something that apps don't really let you do, you can code your scraper. You can do it directly in R or Python or Bash or even Java or PHP. Now, what you're going to do is you're going to be looking for information on the web page. If you're looking for HTML text, what you're going to do is you're going to pull structured text from web pages, similar to how a reader view works in a browser. It uses HTML tags on the web page to identify what's the important information. So that's things like body and H1 for header 1 and P for paragraph in the angled brackets. You can also get information from HTML tables, although this is a physical table of rows and columns I'm showing you. This also uses HTML table tags. That's like table and TR for table row and TD for table data. That's a cell. The trick is when you're doing this, you need the table number, and sometimes you just have to find that through trial and error. Let me give you an example of how this works. Let's take a look at this Wikipedia page on the Iron Chef America competition. I'm going to go to the web right now and show you that one. So here we are in Wikipedia, Iron Chef America. And if you scroll down a little bit, you see we got a whole bunch of text here, and we got our table of contents. And then we come down here, we have a table that lists the winners, the statistics for the winners. And let's say we want to pull that from this web page into another program for us to analyze. Well, there's an extremely easy way to do this with Google Sheets. All we need to do is open up a Google Sheet, and in cell A1 of that Google Sheet, we paste in this formula. It's import HTML, then you give the web page, then you say that you're importing a table. You have to put that stuff in quotes, and the index number for the table. I had to poke around a little bit to figure out that this one was table number 2. So let me go to Google Sheets and show you how this works. Here I have a Google Sheet, and right now it's got nothing in it, but watch this. If I come here to this cell and I simply paste in that information, all this stuff just sort of magically propagates into the sheet, makes it extremely easy to deal with. And now I can, for instance, save this as a CSV file, put it in another program, lots of options. And so this is one way that I'm scraping the data from a web page because I didn't use an API, but I just use a very simple one-line command in Google Sheets to get the information. Now that was an HTML table. You can also scrape data from PDFs. You have to be aware of whether it's a native PDF, I call that a text PDF, or a scanned or image PDF. And what it does with native PDFs is it looks for text elements. Again, those are like code that indicates this is text. And you can deal with raster images, that's pixel images, or vector, which draws the lines, and that's what makes them infinitely scalable in many situations. And then in PDFs, you can deal with tabular data, but you probably have to use a specialized program like Scraper, Wiki, or Tabula in order to get that. And then finally, media like images and video and audio. Getting images is easy. You can download them in a lot of different ways. And then if you want to read data from them, say for instance, you have a heat map of a country, you can go through it, but you'll probably have to write a program that loops through the image pixel by pixel to read the data and then encode it numerically into your statistical program. Now that's my very brief summary, and let's summarize that. First off, if the data you're trying to get at doesn't have an existing API, you can try scraping. And you can use specialized apps for scraping, or you can write code in a language like R or Python. But no matter what you do, be sensitive to issues of copyright and privacy so you don't get yourself in hot water, but instead you make an analysis that can be of great use to you or to your client. The next step in data sourcing is making data. And specifically, we're talking about getting new data. I like to think of this as you're getting your hands on and you're getting data de novo, new data. So, can't find the data that you need for your analysis? Well, one simple solution is do it yourself. And we're going to talk about a few general strategies used for doing that. Now, these strategies vary on a few dimensions. First off is the role. Are you passive and simply observing stuff that's happening already? Or are you active where you play a role in creating the situation to get the data? And then there's the QQ question, and that is, are you going to get quantitative or numerical data? Or are you going to get qualitative data, which usually means text, paragraphs, sentences, as well as things like photos and videos and audio. And also, how are you going to get the data? Do you want to get it online or do you want to get it in person? Now, there's other choices than these, but these are some of the big delineators of the different methods. When you look at those, you get a few possible options. Number one is interviews, and I'll say more about those. Another one is surveys. A third one is card sorting. And the fourth one is experiments, although I actually want to split experiments into two kinds of categories. The first one is laboratory experiments, and that's in-person projects where you shape the information or an experience for the participants as a way of seeing how that involvement changes their reactions. It doesn't necessarily mean that you're a participant, but you create the situation. And then there's also A/B testing. This is automated online testing of two or more variations on a web page. It's a very, very simple kind of experimentation that's actually very useful for optimizing websites. So, in sum, from this very short introduction, make sure you can get exactly what you need. Get the data you need to answer your question. And if you can't find it somewhere, then make it. And as always, you have many possible methods, each of which have their own strengths and their own compromises. And we'll talk about each of those in the following sections. The first method of data sourcing where you're making new data that I want to talk about is interviews. And that's not because it's the most common, but because it's the one you would do for the most basic problem. Now, basically, an interview is nothing more than a conversation with another person or a group of people. And the fundamental question is, why do interviews as opposed to doing a survey or something else? Well, there's a few good reasons to do that. Number one, you're working with a new topic and you don't know what people's responses will be or how they'll react. And so you need something very open-ended. Number two, you're working with a new audience. You don't know how they will react in particular to what it is you're trying to do. And number three, something's going on with the current situation. It's not working anymore, and you need to find what's going on and you need to find ways to improve. The open-ended information where you get past your existing categories and boundaries can be one of the most useful methods for getting that data. If you want to put it another way, you want to do interviews when you don't want to constrain responses. Now, when it comes to interviews, you have one very basic choice, and that's whether you do a structured interview. And with a structured interview, you have a predetermined set of questions, and everyone gets the same questions in the same order. It gives a lot of consistency, even though the responses are open-ended. And then you can also have what's called an unstructured interview. And this is a whole lot more like a conversation where you as the interviewer and the person you're talking to, your questions arise in response to their answers. Consequently, an unstructured interview can be different for each person that you talk to. Also, interviews are usually done in person, but not surprisingly, they can be done over the phone or often online. Now, a couple of things to keep in mind about interviews. Number one is time. Interviews can range from just a few minutes to several hours per person. Second is training. Interviewing is a special skill that usually requires specific training. Now, asking the questions is not necessarily the hard part. The really tricky part is the analysis. The hardest part of interviews by far is analyzing the answers for themes and way of extracting the new categories and the dimensions that you need for your further research. The beautiful thing about interviews is they allow you to learn things that you never expected. So, in sum, interviews are best for new situations or new audiences. On the other hand, they can be time-consuming, and they also require special training both to conduct the interview, but even more to analyze the highly qualitative data that you get from them. An interesting topic in data sourcing when you're making data is card sorting. Now, this isn't something that comes up very often in academic research, but in web research, this can be a really important method. Think of it as what you're trying to do is like building a model of a molecule here. You're trying to build a mental model or a model of people's mental structures. Put more specifically, how do people organize information intuitively? And also, how does that relate to the things that you're doing online? Now, the basic procedure goes like this. you take a bunch of little topics and you write each one on a separate card. And you can do this physically with like 3x5 cards, or there's a lot of programs that allow you to do a digital version of it. Then what you do is you give this information to a group of respondents, and the people sort those cards. So they put similar topics with each other, different topics over here, and so on. And then you take that information, and from that, you're able to calculate what's called dissimilarity data. Think of it as like the distance or the difference between various topics. And that gives you the raw data to analyze how things are structured. Now, there are two very general kinds of card sorting tasks. They're generative and there's evaluative. A generative card sorting task is one in which respondents create their own sets, their own piles of cards using any number of groupings they like. And this might be used, for instance, to design a website. If people are going to be looking for one kind of information next to another one, then you want to put that together on the website so they know where to expect it. On the other hand, if you've already created a website, then you can do an evaluative card sorting. This is where you have a fixed number or fixed names of categories, like for instance, the way you've set up your menus already. And then what you do is you see if people naturally put the cards into these various categories that you've created. That's a way of verifying that your hierarchical structure makes sense to people. Now, whichever method you do, generative or evaluative, what you end up with when you do a card structure is an interesting kind of visualization. It's called a dendrogram. That actually means branches. And what we have here is actually 150 data points. If you're familiar with Fisher's iris data, that's what's going on here. And it groups it from one giant group on the left and then splits it in pieces and pieces and pieces until you end up with lots of different individual level observations at the end. But you can cut things off into 2 or 3 groups or wherever it's most useful for you here as a way of visualizing the entire collection of similarity or dissimilarity between the individual pieces of information that you had people sort. Now, I'll just mention very quickly, if you want to do digital card sorting, which makes your life infinitely easier because keeping track of physical cards is really hard, you can use something like Optimal Workshop or UserZoom or UX Suite. These are some of the most common choices. Now, let's just sum up what we've learned about card sorting in this extremely brief overview. Number one, card sorting allows you to see intuitive organization of information in a hierarchical format. You can do it with physical cards, or you also have digital choices for doing the same thing. And when you're done, you actually get this hierarchical or branched visualization of how the information is structured and related to each other. When you're doing your data sourcing and you're making data, sometimes you can't get what you want through the easy ways, and you got to take the hard way. And you can do what I'm calling laboratory experiments. Now, of course, when I mention laboratory experiments, people start to think of stuff like, Dr. Frankenstein in his lab, but lab experiments are less like this. And in fact, they're a little more like this. Nearly every experiment I have done in my career has been a paper and pencil one with people in a well-lighted room, and it's not been the threatening kind. Now, the reason you do a lab experiment is because you want to determine cause and effect. And this is the single most theoretically viable way of getting that information. Now, what makes an experiment is the fact that researchers play active roles in experiments with manipulations. Now, people get a little freaked out when they hear manipulations, think that you're coercing people and messing with their mind. All that means is you are manipulating the situation. You're causing something to be different for one group of people or one situation than another. It's a benign thing, but it allows you to see how people react to those different variations. Now, you're going to want to do an experiment. You're going to want to have focused research. It's usually done to test one thing or one variation at a time. And it's usually hypothesis driven. Usually you don't do an experiment until you've done enough background research to say, I expect people to react this way to this situation and this way to the other. A key component of all of this is that experiments almost always have random assignments. So regardless of how you got your sample, when they're in your study, you randomly assign them to one condition or another. And what that does is it balances out the pre-existing differences between groups. And that's a great way of taking care of confounds and artifacts, the things that are unintentionally associated with differences between groups that provide alternate explanations for your data. If you've done good random assignment and you have large enough people, then those confounds and artifacts are basically minimized. Now, some places where you're likely to see laboratory experiments in this version are, for instance, eye tracking and web design. That's where you have to bring people in front of a computer and you stick a thing there that sees where they're looking. That's how we know, for instance, that people don't really look at ads on the side of web pages. Another very common place is research in medicine and education, and in my field, psychology. And in all of these, what you find is that experimental research is considered the gold standard for reliable, valid information about cause and effect. On the other hand, while it's a wonderful thing to have, it does come at a cost. Here's how that works. Number one, experimentation requires extensive specialized training. It's not a simple thing to pick up. Two, experiments are often very time-consuming and labor-intensive. I've known some that take hours per person. And number three, experiments can be very expensive. So what that all means is you want to make sure that you've done enough background research, and you need to have a situation where it's sufficiently important to get really reliable cause and effect information to justify these costs for experimentation. In sum, laboratory experimentation is generally considered the best method for causality or assessing causality. That's because it allows you to control for confounds through randomization. On the other hand, it can be difficult to do, so be careful and thoughtful when considering whether you need to do an experiment and how to actually go about doing it. There's one final procedure I want to talk about in terms of data sourcing and making new data. It's a form of experimentation. It's simply called A/B testing, and it's extremely common in the web world. So for instance, I just barely grabbed a screenshot of Amazon.com's homepage, and you've got these various elements on the homepage. And I just noticed, by the way, when I did this, that this woman is actually a animated GIF. So she moves around. That was kind of weird. Never seen that before. But the thing about this is this entire layout, how things are organized and how they're on there, will have been determined by variations on A/B testing by Amazon. Here's how it works. For your web page, you pick one element, like what's the headline or what are the colors or what's the organization or how do you word something, and you create multiple versions, maybe just two, version A and version B, which is why you called A/B testing. And then when people visit your web page, you randomly assign those visitors to one version or another. You have software that does that for you automatically. And then you compare the response rates on some response. I'll show you those in a second. And then once you have enough data, you implement the best version. You sort of set that one solid, and then you go on to something else. Now, in terms of response rates, there's a lot of different outcomes you can look at. You can look at how long a person's on a page. You can actually do mouse tracking if you want to. You can look at click-throughs. You can also look at shopping cart value or abandonment. A lot of possible outcomes. All of these contribute through A/B testing to the general concept of website optimization, to make your website as effective as it can possibly be. Now, the idea also is that this is something you're going to do a lot. You can perform A/B tests continually. In fact, I've seen one person say that what A/B testing really stands for is always be testing. Kind of cute, but it does give you the idea that improvement is a constant process. Now, if you want some software to do A/B testing, two of the most common choices are Optimizely and VWO, which stands for Visual Web Optimizer. Now, many others are available, but these are especially common. And when you get the data, you're going to use statistical hypothesis testing to compare the differences, or really, the software does it for you automatically, but you may want to adjust the parameters because most software packages cut off testing a little too soon and the information is not quite as reliable as it should be. But in sum, here's what we can say about A/B testing. It's a version of website experimentation. It's done online, which makes it really easy to get a lot of data very quickly. It allows you to optimize the design of your website for whatever outcome is important to you. And it can be done as a series of continual assessments, testing, and development to make sure that you're accomplishing what you want to as effectively as possible for as many people as possible. The next logical step in data sourcing and making data is surveys. Now, think of this. If you want to know something, just ask. That's the easy way. And you want to do a survey under certain situations. The real question is, do you know your topic and your audience well enough to anticipate their answers, to know what the range of their answers and the dimensions and the categories that are going to be important? If you do, then a survey might be a good approach. Now, just as there were a few dimensions for interviews, there's a few dimensions for surveys. You can do what's called a closed-ended survey. That's also called a forced choice. It's where you give people just particular options like a multiple choice. You can have an open-ended survey where you have the same questions for everybody, but you allow them to write in a free-form response. You can do surveys in person, and you can also do them online or over the mail or phone or however. And now it's very common to use software when doing surveys. Some really common applications for online surveys are SurveyMonkey and Qualtrics, or at the very simple end, there's Google Forms, and at the simple and pretty end, there's Typeform. There's a lot more choices, but these are some of the major players in how you can get data from online participants in survey format. Now, the nice thing about surveys is, they're really easy to do. They're very easy to set up, and they're really easy to send out to large groups of people. You can get tons of data really fast. On the other hand, the same way that they're easy to do, they're also really easy to do badly. The problem is that the questions you ask, they can be ambiguous, they can be double-barreled, they can be loaded, and the response scales can be confusing. So if you say, I never think this particular way, and a person puts strongly disagree, they may not know exactly what you're trying to get at. So you have to take special effort to make sure that the meaning is clear, unambiguous, and that the rating scale, the way that people respond, is very clear and they know where their answer falls. Which gets us into one of the things about people behaving badly, and that is beware the push-pull. Now, especially during election time, like we're in right now, a push-pull is something that sounds like a survey, but really what it is a very biased attempt to get data, just fodder for social media campaigns, or I'm going to make a chart that says that 98% of people agree with me. A push-pull is one that's so biased, there's really only one way to answer to the questions. This is considered extremely irresponsible and unethical from a research point of view. Just hang up on them. Now, aside from that egregious violation of research ethics, you do need to do other things like watch out for bias in the question wording, in the response options, and also in the sample selection, because any one of those can push your responses off one way or another without you really being aware that it's happening. So in sum, let's say this about surveys. You can get lots of data quickly. On the other hand, it requires familiarity with the possible answers in your audience, so you know sort of what to expect. And no matter what you do, you need to watch for bias to make sure that your answers are going to be representative of the group that you're really concerned about understanding. The very last thing I want to talk about in terms of data sourcing is to talk about the next steps. And probably the most important thing is, don't just sit there. I want you to go and see what you already have. Try to explore some open data sources. And if it helps, check with a few data vendors. And if those don't give you what you need to do your project, then consider making new data. Again, the idea here is get what you need and get going. Thanks for joining me, and good luck on your own projects. Welcome to Coding in Data Science. I'm Bart Poulson, and what we're going to do in this series of videos is we're going to take a little look at the tools of data science. So I'm inviting you to know your tools, but probably even more important than that is to know their proper place. Now, I mention that because a lot of the times when people talk about data tools, they talk about it as though that were the same thing as data science, as though they were the same set. But I think if you look at it for just a second, that's not really the case. Data tools are simply one element of data science, because data science is made up of a lot more than the tools that you use. It includes things like business knowledge. It includes the meaning making and interpretation. It includes social factors. And so there's much more than just the tools involved. That being said, you will need at least a few tools. And so we're going to talk about some of the things that you can use in data science if it works well for you. In terms of getting started, the basic things, Number one is spreadsheets. It's the universal data tool, and I'll talk about how they play an important role in data science. Number two is a visualization program called Tableau. There's Tableau Public, which is free, and there's Tableau Desktop, and there's also something called Tableau Server. But Tableau is a fabulous program for data visualization, and I'm convinced for most people provides the great majority of what they need. And though, while it's not a tool, I do need to talk about the formats used in web data because you have to be able to navigate that when doing a lot of data science work. Then we can talk about some of the essential tools for data science. Those include the programming language R, which is specifically for data. There's the general purpose programming language Python, which has been well adapted to data. And there's the database language SQL, or SQL for a structured query language. Then if you want to go beyond that, there are some other things that you can do. There are the general purpose programming languages C, C++, and Java, which are very frequently used to form the foundation of data science, and sort of high-level production code is going to rely on those as well. There's the command line interface language Bash, which is very common as a very quick tool for manipulating data. And then there's the sort of wildcard, supercharged regular expressions, or regex. We'll talk about all of these in separate courses. But as you consider all the tools that you can use, don't forget the 80-20 rule, also known as the Pareto principle. And the idea here is that you're going to get a lot of bang for your buck out of a small number of things. And I'm going to show you a little sample graph here. Imagine that you have 10 different tools, and we'll call them A through B. A does a lot for you, B does a little bit less, and it kind of tapers down to you've got a bunch of tools that do just a little bit of stuff that you need. Now, instead of looking at the individual effectiveness, look at the cumulative effectiveness. How much are you able to accomplish with a combination of tools? Well, the first one's right here at 60% where the tool started. Then you add on the 20% from B and it goes up, and then you add on C and D, and you add up little smaller pieces. And by the time you get to the end, you've got 100% of effectiveness from your 10 tools combined. The important thing about this is you only have to go to the second tool. That's 2 out of 10. So that's B, that's 20% of your tools. And in this made up example, you've got 80% of your output. So 80% of the output from 20% of the tools. That's a fictional example of the Pareto principle, but I find in real life it tends to work something approximately like that. And so you don't necessarily have to learn everything, and you don't have to learn how to do everything in everything. Instead, you want to focus on the tools that will be most productive, and specifically most productive for you. So in sum, let's say these 3 things. Number 1, coding, or simply the ability to manipulate data with programs and computers. Coding is important, but data science is much greater than the collection of tools that's used in it. And then finally, as you're trying to decide what tools to use and what you need to learn and how to work, remember the 80-20 rule. You're going to get a lot of bang from a small set of tools, so focus on the things that are going to be most useful for you in conducting your own data science projects. As we begin our discussion of coding and data science, I actually want to begin with something that's not coding. I want to talk about applications, or programs that are already created that allow you to manipulate data. And we're going to begin with the most basic of these, spreadsheets. We're going to do the rows and columns and cells of Excel. And the reason for this is you need spreadsheets. Now, you may be saying to yourself, no, not me. Because you know what? I'm fancy. I'm working in my big set of servers. I got fancy things going on. But you know what? You too, fancy people, you need spreadsheets as well. And there's a few reasons for this. Most importantly, spreadsheets can be the right tool for data science in a lot of circumstances. There are a few reasons for that. Number 1, spreadsheets, they're everywhere. They're ubiquitous. They're installed on 1 billion machines around the world. And everybody uses them. They probably have more data sets in spreadsheets than anything else. And so it's a very common format. Importantly, it's probably your client's format. A lot of your clients are going to be using spreadsheets for their own data. I've worked with billion-dollar companies that keep all of their data in spreadsheets. And so when you're working with them, you need to know how to manipulate that and how to work with it. Also, regardless of what you're doing, spreadsheets, or specifically CSV comma-separated value files, are sort of the lingua franca, the universal interchange format for data transfer to allow you to take it from one program to another. And then, truthfully, in a lot of situations, they're really easy to use. And if you want a second opinion on this, let's take a look at this ranking that is a survey of data mining experts. It's the KD Nuggets data mining poll. And these are the tools they most use in their own work. And look at this. Lowly Excel is 5th on the list. And in fact, what's interesting about it, it's above Hadoop and Spark, two of the major big data fancy tools. And so Excel really does have a place of pride in a toolkit for a data analyst. Now, since we're going to sort of the low-tech end of things, let's talk about some of the things that you can do with a spreadsheet. Number one, they're really good for data browsing. You actually get to see all of the data in front of you, which isn't true if you're doing something like R or Python. They're really good for sorting data. Sort by this column, then this column, then this column. They're really good for rearranging columns and cells and moving things around. They're good for finding and replacing and seeing what happened so you know that it worked right. Some more uses. They're really good for formatting, especially conditional formatting. They're good for transposing data, switching the rows and the columns. They make that really easy. They're good for tracking changes. Now, it's true if you're a big fancy data scientist, you're probably using GitHub. But for everybody else in the world, spreadsheets and the tracking changes is a wonderful way to do it. You can make pivot tables. That allows you to explore the data in a very hands-on way, in a very intuitive way. And they're also really good for arranging the output for consumption. Now, when you're working with spreadsheets, however, there's one thing you need to be aware of. They're really flexible, but that flexibility can be a problem, and that when you're working in data science, you specifically want to be concerned about something called tidy data. That's a term I borrowed from Hadley Wickham, very well-known developer in the R world. Tidy data is for transferring data and making it work well. There's a few rules here that undo some of the flexibility inherent in spreadsheets. Number one, what you want to do is have a column be equivalent to the same thing as a variable. Columns, variables, they are the same thing. And then rows are equal, exactly the same thing as cases. And that you have one sheet per file, and that you have one level of measurement, say individual, then organization, then state, per file. Again, this is undoing some of the flexibility that's inherent in spreadsheets, but it makes it really easy to move the data from one program to another. Let me show you how all this works. You can try this in Excel. If you've downloaded the files for this course, we simply want to open up this spreadsheet. Let me go to Excel and show you how it works. So when you open up the spreadsheet, what you get is totally fictional data here that I made up, but it's showing sales over time of several products at two locations, like if you're selling stuff at a baseball field. And this is the way spreadsheets often appear. We got blank rows and columns. We got stuff arranged in a way that makes it easy for the person to process it. And we got totals here and with formulas, putting them all together. And that's fine. That works well for the person who made it. And then that's for 1 month. And then we have another month right here. And then we have another month right here. And then we combine them all for the first quarter of 2014. We've got some headers here, and we've got some conditional formatting and changes. And if we come to the bottom, we've got a very busy line graphic that eventually loads. It's not a good graphic, by the way, but similar to what you will often find. So this is the stuff that, while it may be useful for the client's own personal use, you can't feed this into R or Python. It'll just choke and it won't know what to do with it. And so you need to go through a process of tidying up the data. And what this involves is undoing some of this stuff. So for instance, here's data that is almost tidy. Here we have a single column for the date, a single column for the day, a column for the site. So we have two locations, A and B. And then we have 6 columns for the 6 different things that are sold and how many were sold on each day. Now, in certain situations, you would want the data laid out exactly like this. If you're doing, for instance, a time series, you'll do something vaguely similar to this. But for true tidy stuff, we're going to collapse it even further. Let me come here to the tidy data. And now what I've done is I've created a new column that says, what is the item being sold? And so, by the way, what this means is that we've got a really long data set now. It's got over 1,000 rows. Come back up to the top here. But what that shows you is that now it's in a format that's really easy to import from one program to another. That makes it tidy, and you can remanipulate it however you want once you get to each of those. So let's sum up our little presentation here in a few lines. Number one, no matter who you are, no matter what you're doing in data science, you need spreadsheets. And the reason for that is that spreadsheets are often the right tool for data science. Keep one thing in mind though, and that is as you're moving back and forth from one language to another, tidy data or well-formatted data is going to be important for exporting data into your analytical programmer language of choice. As we move through coding and data science, and specifically the applications that can be used, there's one that stands out for me more than almost anything else, and that's Tableau and Tableau Public. Now, if you're not familiar with these are visualization programs. The idea here is that when you have data, the most important thing you can do is to first look and see what you have and work with it from there. And in fact, I'm convinced that for many organizations, Tableau might be all that they really need. It will give them the level of insight that they need to work constructively with data. So let's take a quick look by going to tableau.com. Now there are a few different versions of Tableau. Right here we have Tableau Desktop and Tableau Server, and these are the paid versions of Tableau. They actually cost a lot of money, unless you work for a nonprofit organization, in which case you can get them for free, which is a beautiful thing. What we're usually looking for, however, is not this paid version, but we're looking for something called Tableau Public. And if you come in here and go to Products, and we've got these three paid ones, come over here to Tableau Public. And we click on that, it brings us to this page. It's public.tableau.com. And this is the one that has what we want. It's a free version of Tableau with one major caveat. You don't save files locally to your computer, which is why I didn't give you a file to open. Instead, it saves them to the web in a public forum. So if you're willing to trade privacy, you can get an immensely powerful application for data visualization. That's a catch for a lot of people, which is why people are willing to pay a lot of money for the desktop version. And again, if you work for a nonprofit, you can get the desktop version for free. But I'm going to show you how things work in Tableau Public. So that's something that you can work with personally. The first thing you want to do is you want to download it. And so you put in your email address, you download, it's going to know what you're on. It's a pretty big download. And once it's downloaded, you can install it and open up the application. And here I am in Tableau Public right here. This is the blank version. By the way, you also need to create an account with Tableau in order to save your stuff online and to see it. We'll show you what that looks like. But you're presented with a blank thing right here. And the first thing you need to do is you need to bring in some data. I'm going to bring in an Excel file. Now, if you've downloaded the files for the course, you'll see that there's this one right here, DSO322 Tableau Public. .xlsx. It's a Excel file, and in fact, it's the one that I used in talking about spreadsheets in the first video in this course. I'm going to select that one, and I'm going to open it. And a lot of programs don't like bringing in Excel because it's got all the worksheets and all the weirdness in it. This one works better with it, but what I'm going to do is I'm going to take the tidy data. By the way, you see that it put them in alphabetical order here. And I'm going to take tiny data, and I'm just going to drag it over to let it know that it's the one that I want. And now what it does is it shows me a version of the data set along with things that you can do here. You can rename it. You can create bin groups. There's a lot of things that you can do here. I'm going to do something very, very quick with this particular one. Now I've got the data set right here. What I'm going to do now is I'm going to go to a worksheet. That's where you actually create stuff. Cancel that and go to worksheet 1. Okay, this is a drag and drop interface. And so what we're going to do is we're going to pull the bits and pieces of information we want. to make graphics. There's immense flexibility here. I'm going to show you two very basic ones. I'm going to look at the sales of my fictional ballpark items. So I'm going to grab sales right here. And I'm going to put that as the field that we're going to measure. Okay, and you see it put it down right here. And this is our total sales. We're going to break it down by item and by time. So let me take item right here. And you can drag it over here, or I can put it right up here into rows. Those will be my rows, and that's how many we've sold total of each of the items. Fine, that's really easy. And then let's take date, and we'll put that here in columns to spread it across. Now, by default, it's doing it by year. I don't want to do that. I only have 3 months of data. And so what I can do is I can click right here, and I can choose a different time frame. I can go to quarter, but that's not going to help because I only have 1 quarter's worth of data. That's 3 months. I'm going to come down to week. Actually, let me go to day. If I do day, you see it gets enormously complicated, so that's no good. So I'm going to back up to week. And I've got a lot of numbers there, but what I want is a graph. And so to get that, I'm going to come over here and click on this and tell it that I want a graph. And so we're seeing the information, except it lost item. So I'm going to bring item and I'm going to put it back up into this graph to say this is a row for the data. And now I've got rows for sales by week for each of my items. That's great. I want to break it down one more by putting in the site, the place that it's sold. And so I'm going to grab that and I'm going to put it right over here. And now you see I've got it broken down by the item that is sold and the different sites. And I'm going to color the sites. And all I got to do to that is I'm going to grab site and drag it onto color. Now I've got 2 different colors for my sites. And this makes it a lot easier to tell what's going on. And in fact, there's some other cool stuff you can do. One of the things I'm going to do is I can come over here to analytics and I can tell it, for instance, to put an average line through everything. So I'll just drag this over here and say, now we have the average for each line. That's good. And I can even do forecasting. Let me get a little bit of a forecast right here. I'll drag this on. And if you go over here, I can get this out of the way for a second. Now I have a forecast for the next few weeks. And that's a really convenient, quick and easy thing. And again, for some organizations, that might be all that they really need. And so what I'm showing you here is the absolute basic operation of Tableau, which allows you to do an incredible range of visualizations and manipulate the data and create interactive dashboards. There's so much to it, and we'll show that in another course. But for right now, I want to show you one last thing about Tableau Public, and that is saving the files. So now when I come here and save it, it's going to ask me to sign into Tableau Public. Now I sign in, and it asks me how I want to save this. Same name as the video. There we go, and I'm going to hit save. And then that opens up a web browser. And since I'm already logged into my account, see, here's my account, my profile. Here's the page that I created. And it's got everything I need there. I'm going to edit just a few details. I'm going to say, for instance, I'm going to leave its name like that. I could put more of a description in there if I wanted. I can allow people to download the workbook and its data. I'm going to leave that there so you can download it if you need to. If I had more than one tab, I would do this thing that says show the different sheets as tabs. Hit save. And there's my data set. And also, it's published online and people can now find it. And so what you have here is an incredible tool for creating interactive visualizations. You can create them with drop-down menus and you can rearrange things and you can make an entire dashboard. It's a fabulous way of presenting information. And as I said before, I think that for some organizations, this may be as much as they need to get really good, useful information out of their data. And so I strongly recommend that you take some time to explore with Tableau, either the paid desktop version or the public version, and see what you can do to get some really compelling and insightful visualizations out of your work in data science. For many people, their first experience of coding in data science is with the application SPSS. Now, I think of SPSS, and the first thing that comes to my mind is sort of life in the ivory tower, though this looks more like, Harry Potter. But if you think about it, the package name SPSS comes from Statistical Package for the Social Sciences, although if you ask IBM about it now, they'll act like it doesn't stand for anything. But it has its background in social science research, which is generally academic. And truthfully, I'm a social psychologist, and that's where I first learned how to use SPSS. But let's take a quick look at their webpage, ibm.com/SPSS. If you type that in, that'll just be an alias that'll take you to IBM's main webpage. Now, IBM didn't create SPSS, but they bought it around version 16, and it was very briefly known as PASW, Predictive Analytics Software. That only lasted briefly, and now it's back to SPSS, which is where it's been for a long time. SPSS is a desktop program. It's pretty big. It does a lot of things. It's very powerful. It's used in a lot of academic research. It's also used in a lot of business consulting, management, and even some medical research. And the thing about SPSS is it looks like a spreadsheet, but it has drop-down menus to make your life a little bit easier compared to some of the programming languages that you can use. Now, you can get a free temporary version. If you're a student, you can get a cheap version. Otherwise, SPSS costs a lot of money. But if you have it one way or the other, when you open it up, this is what it's going to look like. I'm showing SPSS version 22. Now, it's currently on 24. And the thing about SPSS versioning is in any other software package, these would be point updates. So I sort of feel like we should be on 17.3 as opposed to 22 or 24, because the variations are so small that anything you learn from the earlier ones is going to work in the later ones. And there's a lot of backwards and forwards compatibility. So I'd almost say that this one, the version you have, practically doesn't matter. You get this little welcome splash screen, and if you don't want to see it anymore, you can get rid of it. I'm just going to hit cancel here. And this is our main interface. Looks a lot like a spreadsheet. The difference is you have a separate pane for looking at variable information, and then you have separate windows for output, and then an optional one for something called syntax. But let me show you how this works by first opening up a data set. SPSS has a lot of sample data sets in them, but they're not easy to get to, and they're really well hidden. On my Mac, for instance, let me go to where they are. In my Mac, I go to the Finder. I have to go Mac to Applications, to the folder IBM, to SPSS, to Statistics, to 22, the version number, to Samples. Then I have to say I want the ones that are in English, and then it brings them up. The .sav files are the actual data files. There are different kinds in here. So .sps is a different kind of file. And then we have a different one about planning analyses. So there are versions of it. I'm going to open up a file here called marketvalues.sav. It's a small data set in SPSS format. And if you don't have that, you can open up something else. It really doesn't matter for now. By the way, in case you haven't noticed, SPSS tends to be really, really slow when it opens. It also, despite being at version 24, tends to be kind of buggy and crashes. And so when you work with SPSS, you want to get in the habit of saving your work constantly and also being patient when it's time to open the program. So here's a data set that just shows addresses and house values and square feet for some information. This, I don't even know if this is real information. It looks artificial to me. But SPSS lets you do point and click analyses, which is unusual for a lot of things. So I'm going to come up here and I'm going to say, for instance, make a graph. I'm actually going to use what's called a legacy dialog to get a histogram of house prices. So I simply click values, put that right there, and I'll put a normal curve on top of it and hit OK. And then it's going to open up a new window, and it opened up a microscopic version of it here. So I'm going to make that bigger. This is the output window. And so this is a separate window, and it has a navigation pane here on the side. It tells me where the data came from, and it saves the command here. And then, there's my default histogram. And so we see most of the houses were right around $125,000, and then they went up to at least 400,000. I have a mean of 256,000, a standard deviation of about 80,000, and there's 94 houses in the data set. Fine, that's great. The other